So I want to talk a little bit about where continuous delivery comes from, why it works, and who applies it and why. And it's my contention that if you look at the history of the software development industry, the story is pretty poor. We haven't really done very well. These are results of various surveys that have been carried out over the years of all different kinds of surveys, all different kinds of projects. And it's generally, when you look at these sorts of things, it's usually pretty much a tale of life. If software development process was a normal thing, we'd have a normal distribution of projects that project success. There would be some failures, there'd be some things that succeeded way beyond visions, and then there'd be a norm in the middle somewhere, and be able to predict what's going on. It doesn't look like that. If you plot it, it doesn't look anything like that at all. This kind of amuses me and horrifies me in equal measure. This last one. In a study of over 5,000 large-scale projects, 70% of the projects went so badly that they threatened the existence of the company that undertook it. That's kind of the state of the industry that we work in. I would kind of argue that the state of software development is sort of suboptimal. Well, I believe that there are signs of change. Actually, what I believe is that we know how to do this. I think it's software development to solve the problem, but it's not evenly spread. Most organisations are not applying the techniques that we now know work. So the rest of my talk really is to try and describe the ways in which, what it takes to make this stuff work, and the data that kind of backs up this contention. So what have we tried over the years? So we've looked at other industries and we've tried to take process from those industries, and we've kind of taken the waterfall model and the V model, and we've tried organisations built as silos where we throw things over the wall between different things. If there were anybody old enough to remember things like Rock, we started more iterative approaches, trying to break things down. Scrum, looking at ways in which we could organise ourselves as teams. We've tried extreme programming. We've tried hiring really smart people and putting them in a corner and seeing how that played out. We tried hiring young smart people and putting them in a corner because they're cheaper. We've tried hiring young smart people in foreign countries because they're even cheaper. And all of these kind of approaches sort of have something to them, something, at least something to learn from. And learning, as you get from my keynote, I think learning is important. So here's a sequence of events. You can see the keynote, that's the accident, there's a car falling off the dock. This is somewhere in Ireland. So what do you do now? The crane's falling in, you get a bigger crane. Yay, you've got the car. Now you try and get Einstein said that insanity is doing the same thing over and over again and expecting different results. So if our software development processes have not really been fulfilling the promise that we wanted them, we should try something different. We should try anything different if they're not really working. So what is it that we really want? What is it that everybody involved in software development of any kind really wants? What they really want is that they want to have an idea, they want to get that idea in the form of working software into the hands of users, and they want to figure out what the users make of it. That's what every business, every organisation that employs us wants. And that's what our job as software professionals should be, to deliver on that dream, on that goal, on that promise. My guess is that given my presentation this morning, you can guess what my answer to this question is. So classically, I kind of put this up and say, well, what do you think? Maybe the invention. Well, I kind of gave the punchline away a little bit this morning. So I think science is human beings, humankind's greatest invention. I think it's our best discovery. It's by far our strongest problem-solving technique. And this is the scientific method that we talked about this morning. So let's look a little bit more in detail about that, the data that kind of backs up the things that I'm saying. So again, you can kind of take these things with a pinch of salt. Most of these sorts of surveys of software projects, the sample size is not generally large enough to really allow statistics and Bayesian analysis and that sort of thing to come into play. They tend to be self-reporting, so if a project thinks that it's agile, they will say it's agile even if they're not agile by the definitions that we might apply, and all those sorts of things. So there are lots of ways in which you can critique these sorts of analyses, but it is really all we've got. You can't really set off a proper scientific experiment with a control for a software project. There are just too many variables. So this is the data that we've got. And this data is from the Chaos Manifesto, which has been reporting on software projects for a very long time now. And this is kind of a common picture. So generally what they say is that waterfall methodologies, so 57% of waterfall projects are challenged, 14% are successful. Agile methodologies, they do better, 42% are successful, and 49% are challenged, but still, 49% of these projects are challenged. Some people say that the Chaos Manifesto data is too pessimistic, and one of the people that says that is Scott Ambler, who's also been collecting data on software projects for a very long time. And this is his data. This is my organisation of his data, and what I've done is that I've kind of put iterative sort of approaches to development on the top line and more traditional waterfall-like approaches on the bottom line. The thing that really amused me the first time I looked at this was that if you make up your process on the spot, it's slightly better than doing traditional waterfall. But as you might expect, for this group of people, as I assume you would all expect, a more agile, iterative approach to development is more effective. And the best looking one is probably lean, where you have a higher percentage rate of success from the data. So what's that all about? What's that talking about? So lean thinking is about delivering quickly. This is getting to the experimental approach that I was talking about this morning. We want to build high quality things all of the time. We don't want to be inspecting quality into the process late in the stage. We want to be concentrating and worrying about quality from the outset. We want to optimise the whole process, not just individual bits of it. We want to take a holistic look at software development and figure out where the bottlenecks are, wherever they may be. And we want to eliminate waste. We want to make this as efficient as possible. We want to amplify learning. We want to concentrate on learning as an objective, and so that we as teams get better and better at what we do, and therefore more efficient and more creative at what we do. We want to free ourselves to do the creative things. That's where the amazing abilities of humans really come to play when we're being creative. And one of the things that kind of helps us do that is to make decisions as late in the process as possible. A good friend of mine paraphrased, you make decisions at the last responsible moment. My wife says that the trouble with that philosophy is that the last responsible moment is milliseconds before the first irresponsible moment. That's the marriage, I think. And you want to empower the team. You want the team to be able to make decisions and figure out for themselves how to solve problems. The people that are doing the work, that are close to the software systems, are the people that will know how to fix the problems as they arise. And so you need to empower other people to make decisions and make choices. You've already seen this picture this morning. Software is a series of interlocking feedback loops, and it's really important when you talk about agile processes to think about these feedback loops. I believe that this is actually much more important than things like stand-ups or Kanban or anything like this. The feedback loops are really what allow you to reflect and react to what's going on. That's really the fundamental nature of agile development, much more than whether your stand-ups are effective or not. I'm a consultant. I see way too many organisations that say they're doing agile because they have stand-ups every morning and then they're going to do waterfall for the rest of the day. Doing this by rote is not good enough. What this is about is learning and adapting and changing. That's really what's at the heart of agile development in general and continuous delivery specifically. So we're looking to at the outside we've got this crucial feedback loop of having an idea and getting it into the hands of our users, and inside we've got the kind of the really fine-grained working of test-driven development where we're writing some codes, we write a test, see it fail, write the code to make it pass, check it in, move on to the next. And here's my Feynman quote again, that it doesn't matter how smart you are if you guess, and that's not backed by experimental evidence, it's still a guess. So we should be looking for ways to verify our choices, to figure out what things that we, when we make a decision, figure out how we will test that decision. One of the really nice tools that kind of we nicked from lean thinking when we started talking about continuous delivery is the idea of cycle time. And cycle time is the idea of, if you imagine the smallest possible change to your production system, and how long would it take you to make that change and validate it in all of the ways that you should and would normally to release your software and get your software into production. And I'm going to show you cycle times from two projects that I've worked on. The first project was from a big bank, and it was when I was a consultant at ThoughtWorks, and we were doing the job for the bank, and they couldn't make any change to their production system in under 103 days. If you have a cycle time of 103 days, you don't have a feedback. If somebody comes to me after 103 days and says, Dave, you broke production with a change, I'm going to say, what change? Oh, I don't remember. The other project is another project that I worked on, and we could make any change to our system, any change, and we could evaluate that change in 57 minutes. If you've got a cycle time of 57 minutes, you can kind of, somebody comes back and says, Dave, you broke production, I'm going to know what was working on 57 minutes ago. Also, if you've got a change of 57 minutes, imagine if you've got a cycle time of 103 days, you've got these big release trains, you've got this huge amount of change that every 50 train is going to be plunked into production. A massively complicated set of changes, a massively risky set of changes which are going to be dropped in production, and when something goes wrong, you've got a nightmare job to figure out what it is that's going wrong, whether it's my change or your change or somebody else's change or a combination. If you're working at this kind of resolution, then my change may be conflated with a couple of other people's changes, but it can be fairly obvious because the change set on this granularity is going to be tiny. It's going to be fresh in our mind because we've just done the work, and it's going to be clear when something goes wrong, what it was that goes wrong. And if we do need to revert, we've only got a tiny step back to revert the change. So this is also a way of reducing risk by thinking that cycle time. As I said in the keynote this morning, I believe that if you apply kind of an experimental approach and the idea of cycle time, look at an analysis of your process and aggressively try to optimize that process, you will end up with all of the good stuff from Agile and Lean and continuous delivery as part of your process. It's kind of an inevitable consequence. And I will describe later an example of parallel evolution where somebody independently came up with continuous delivery by doing exactly what I just described. When I say any change, one of the changes that we made in here was we changed our database vendor. We didn't like the commercial contract that we had with our database vendor. So we switched database vendors and we moved over, wrote the deployment scripts for the new database, we ran it through the pipeline. There were a couple of bugs that were found by our test. We fixed those bugs, we ran it through the pipeline again, and we released. So it took actually 114 minutes, plus the bit of development, the fiddling time in between, to get that change. I've worked at places where a project to change the database vendor on a system that was simpler than the one that I'm describing here would have been a 6-month-long project. So what are we talking about with continuous delivery? So the Agile Manifesto says that continuous delivery is our highest priority. It says our highest priority is to satisfy the customer through early and continuous delivery of valuable software. That's this. Have an idea, get it to the hands of our users and figure out what they're making. There's data that suggests that even in the most successful companies, 2/3 of their ideas produce 0 or negative value for the company. 2/3 create 0 or negative value. If that's the case, the only sensible thing that we can do is optimize our processes and approaches to have lots of ideas and figure out which are the bad ones and throw them away. It's the only sensible thing we can do if that's what's really happening. So, continuous delivery is the first principle of the Agile Manifesto. It's kind of the logical extension of continuous integration. Can I have a show of hands if you're doing continuous integration? Okay, and can you just lift your hands up? So put your hands down if you have multiple branches in your continuous integration system. Put your hands down if you release software with failures in your tests at the end of your continuous integration system. Okay, so that gentleman is doing continuous integration. The rest of you need to put your game a little bit to get there. Continuous integration is about detecting the failures and responding to them. Continuous delivery is also kind of a holistic approach to software development. It's not just about the build or the deployment or the automation of configuration management. It's about the whole process. It's about how change flows through the business. How, if we're trying to optimise from having ideas to being valuable software, we've got to worry about the way that the business works as well as everything else. This has continuous delivery is one of these subversive ideas. It tends to take over organisations. If you look at the organisations that are really good at this stuff, they look very, very different to a more traditional organisation. At all levels, from the way that the CEO interacts to the way that development teams and operations teams, every aspect of the business looks different. Every commit creates a release candidate. This is kind of a nice little thought experiment to think about what's going on. So every time we make a change that is destined for production, imagine that a release candidate is born, and then the rest of our system is going to try and prove that that release candidate is not fit to make it into production. And we've got to build that system to weed out the weak release candidates. And finished means released into production. This is what it says in the book. Actually, this is one of the things that if I was writing it again, I'd slightly reword that. Finished means in the hands of the users delivering value. Released into production isn't enough. In the hands of the users delivering value is really what finished means. So we've got to take this holistic approach. We've got to take this whole picture. So I put this slide up in the earlier presentation, and I want to just walk through this in a little bit more detail. So, if we want to create a repeatable, reliable process for releasing software, that means that we can't depend on humans too much, because we are not repeatable or reliable. We're not very good. A friend of mine, Kevin Henny, said human beings are not good at for loops. We're not good at going over and over and doing the same thing over and over again. Machines are wonderful at that, so we use machines for that stuff. So what that means is that we want to automate nearly everything. We want to leave human beings in the process to do the things that human beings are good at, to make the soft, fuzzy decisions. But all of the hard decisions, the yes-no decisions, we want to automate those. If we want to automate nearly everything, we've got to keep nearly everything under version control. And I don't just mean the source code for our applications, but the configuration of those applications, the dependency on the tools that and infrastructure that they use, the switch state, the switch configuration for your network, maybe. All of that stuff needs to be versioned. So that a good mental thought experiment is: can I go back and run the version of my system that was in production 6 months ago in a test environment? If you can do that, configuration management is good. If you can't do that, there's room to get better. Software is weird. Unlike most of human experience, if things are difficult and painful, it's probably not a bad thing to try and avoid them. In software, if we avoid them, they tend to get worse. So if you're releasing every 6 months and that's a difficult, painful experience, the wrong thing to do is to start releasing every 12 months. It's only going to get worse. What you should do if you're releasing every 6 months is start releasing every 3 months, every month, every week, every 57 minutes. Start getting to that stage where your software is permanently in a releasable state. And that takes effort and time and investment to get to that stage. But when you do, it starts to change the game. It starts to change your relationship with the software that you work with and it's in production. We've already talked about done means released, it means in how you delivering value. The next point, everybody's responsible for the process. Everybody has a stake. The business care because it's their ideas that we're trying to put into production and to deliver value. The testers care because they want to know what's going on when it's in production. Operations care, development teams care, everybody cares. So having tools that make it transparent where change is, if we've got this continual flow of change, we've got to think about ways of managing that are probably a bit different to the normal, more stage-gated approaches to doing it. And we need to look to improve continuously. This is not a process that you say, okay, we've finished implementing continuous delivery, we've done now. Organisations that are good at this stuff have become experimental organisations, and that means they're questioning everything, and they're continually trying new things, and they're continually evolving and changing and adapting and just experimenting. And sometimes experiments work, and sometimes they don't, and they'll go back to what they were doing before. But they'll be trying new things all of the time. This isn't a destination. This is a shift in the way of working. This is just hubris on my part. So this is a quote from Forrester. If Agile software development was the opening act to a great performance, continuous delivery is the headline. Continuous delivery kind of rolls up, because it takes this holistic picture, it kind of rolls up a lot of Agile and lean thinking and kind of puts its arms around it and allows you to think about these things in holistic terms. The nice thing about this is it also uses a vocabulary that's very open to discussing with the business, because our highest priority is the early and continuous delivery of valuable software to users. That's what businesses want. That's not a technical requirement. They probably don't care about the version control aspects and the test automation and all that stuff, the detail of that. That's an implementation detail. But the outcome is exactly what they want. And so we can have conversations at senior levels in organisations and talk about the value that we can bring. And I'll talk more about that later as we go through. What does this look like in the organisations that practice it? Well, they tend to be noisy, collaborative places. These sorts of environments tend to be big on testing ideas. We're trying these experiments and we're trying to evaluate these ideas and try them out. And we tend to have lots of sticky notes everywhere. We tend to have big information radiators showing us the state of our build so we can make it transparent, the changes in the process. We tend to have people working in pairs and collaboratively. We tend to be using lots of data and evaluating what that means and making decisions based on the information that we're gathering. And we tend to be automating, and every time we find something, every time we kind of do something twice, we start questioning why we're doing it the second time. Should we be automating this again? So I want to walk you through that. There's a core idea in continuous delivery called the deployment pipeline, which is I'm going to describe now. One thing to bear in mind is that the deployment pipeline isn't a one-size-fits-all idea. There are different ways in which you can implement deployment pipelines depending on the nature of your project, and this is just one. So I think this kind of represents kind of core principles, and this is based on a real project that I worked for. It was a trading exchange, and the trading exchange had third-party integration points to many tens of different kinds of integrations to different kinds of systems. We had a public web API, binary API, private binary API, web pages. So this wasn't a trivial system. This wasn't a very simple kind of crude web page style system. It was a proper first-class enterprise complex system. So when we start off, we've got developers working together, and they've got some change that they want to commit. So they're going to submit that to some source control repository, and there's going to be a process, we call it the commit build, which is going to be triggered by the change, and we're going to evaluate this. This, so far, is indistinguishable from continuous integration. Okay? That's all I'm talking about so far. What we want from the commit stage is we want fast feedback. We want fail fast. So we want to be able to run tens of thousands of tests in handfuls of minutes to get that fast feedback. That starts to tell you something about the nature of the tests that we want to run. It means that they're going to be in process. We don't want to be instantiating a database or a web server in order to evaluate this code. We want it to be, the test is calling directly to the code in the test. So these are the classic kind of TDD style unit tests, close to the code, very efficient. We can run tens of thousands of them. We get a high degree of confidence that the code is doing what we think. This is the TDD as double entry bookkeeping that I mentioned before. Where we start to differ is we want to keep the results. So as an outcome of this, if all of these tests pass, and only if all of these tests pass, we want to create the releasable artifacts for our system. So whatever technologies we're using, we want to generate the binary images that will be deployed into production. The reason that we want to do that is that we don't want to repeat a step. First of all, it's inefficient. If we've already compiled, so we don't want to go back and compile again, that's inefficient. But more importantly than that, it's also a source of errors. If we compile here, and then at the point at which we're going to release it to production, we recompile again, we might be compiling with different flags. Maybe those flags will introduce a bug that we haven't thought about, and maybe that bug could have been caught by one of the tests that we ran here. So we will have missed an opportunity if we do that. So we want to build one, so we want to keep the results, and we're going to, from now on, we're going to be evaluating against the release candidate that the commit build generates. There are few stronger proponents of test-driven development than me. I think it's a step change in the quality of the work that we produce, that the impact on our designs, it makes us write better code. What it doesn't do is it doesn't really tell us if the code does what the users want it to do. So test-driven development, the unit tests that we create are wonderful at telling developers that the code does what the developers think it should do, but it doesn't say anything really about whether it does what the users want it to do. For that you need more functional tests. And in continuous delivery pilots we call those acceptance tests. We want to run some tests that are going to accept or reject this release candidate. And we want these tests to be as lifelike as we can get. We want them to be running in production-like environments. We want them to be evaluating the software through natural interfaces to the software. We don't want backdoors for testing. We want them to be testing the whole system as far as we can in lifelike circumstances. There are lots of tricks and techniques to getting that right and doing that in a way that's sustainable and maintainable as part of the team over time. I don't have time to cover that in this presentation, but there's some stuff online if you want to dig more deeply, and there's some stuff in the book about that as well. The acceptance test runs will be triggered by release candidates in the artifact repository. Now, an important aspect of this is that this is going to be running in the order of, usually you're targeting in under 5 minutes. Ideally, you want the commit build to be finishing in under 5 minutes. Sometimes technology constraints and so on may push that up, but you don't want it to go. If it starts getting much over 10 minutes, it starts to affect the process. It starts to affect the level of interaction that developers will have with the system, and that impedes the ability to release. So it's kind of a cap on the speediness of this feedback loop for its maximum effectiveness. These tests, we want them to be realistic, lifelike. We want to be starting up real versions of the system. These things can afford to be a bit slow, but we don't want it to be too slow. But this system, we had, when I left the project that this is based on, we had in the order of about 20, we had about 60,000 of these tests, and I think about 20,000 of these tests. And these tests, if you ran them all sequentially, it was over 30 hours worth of testing. but we ran them all in parallel and did some clever tricks to achieve that, and we got results from this in about 40 minutes. So, my job as a developer, I'm going to write some change, I'm going to commit the change, I'm going to sit and wait for the commit build to tell me that it's good. That's going to be a high level of confidence that mostly that means everything's good. And then I'm going to go away and start working on something else. Meanwhile, this thing's going to be running in the background, and I'm kind of keeping half an eye on this to see whether there's a failure. If there's a failure, my job is to drop whatever I'm doing and to go and fix the failure that I've introduced further down the chain. What we're trying to do is that we're trying to optimise to keep the build in a releasable state all of the time. That's our highest priority. When the acceptance tests are run, they're going to decorate the release candidate in the artifact repository with some metadata. They're going to say, these tests all passed. These were the tests that were run against it, and they all passed. Now, I've talked a lot about test automation and its importance and the value of it. And we should be using computers for what they're good at and human beings for what they're good at. It's my contention that human beings doing any form of regression testing is an anti-pattern. We shouldn't do it. Human beings are not good enough at it. They're too expensive, they're too slow, they're too error-prone, they're not reliable enough. But human beings are wonderful at other kinds of tests. They're wonderful at doing exploratory tests. They're wonderful at kind of the subjective sense of whether this system hangs together and is usable and makes a coherent whole. There are things that I would never think to write an automated test for that a human being will pick up immediately. Largely user interface based things, but still those, for many of us, those things are important. So, if I write if I'm doing a web application and I put a white button on the screen with white text on it, you can still click on it, but it's not much use to a human being because they don't know what it's for. An automated test will pass that text. A human being will reject it in the end. So there are those kinds of things. So there's probably, depending on the nature of your application, there's probably room for human testing, and so you want to make that flexible. One of the things that I haven't mentioned so far is deployment. If you want to do this kind of whole system automated testing in production-like environments, you've got to be able to automate the deployment of your application and its configuration. That means that you've got tools that allow you to deploy the application. They should be the same tools that you use when you release it into production. They should be the same tools that you use when you want to deploy to a manual test environment for a human being to interact with the system. This way, by the time we get to the point at which we're going to release the software into production, we've already rehearsed the deployment of this software many times. Precisely this version of the tools, we know it works. It's proved to work. It's already worked multiple times before we get to production. So we want typically we're going to put a little application on top of our deployment tool so that there's a user interface on top of that so the users can choose the release candidates that they want to test and deploy into the environment that they want. That in itself is a huge step for many organisations. That in itself changes your relationship with the software. I remember the first times I did this kind of 10 or 15 years ago, and the change in the way in which people reacted with the software. One place I was working, we were working with a startup, and they were trying to, at the same time that we were building the software, they were trying to get venture capital money and so on. And so they wanted to demo the software. And so we were writing our software so we're keeping it in a releasable state. And they were able to say things like, we've got somebody coming in this afternoon, can you demo it? And we could just say, yeah, sure, and just take it with confidence, just take the latest release candidate and press a button and deploy it, because our deployment system worked. I'd never worked like that before. Before that, having somebody come in to see a demo for a software in development would be a big deal, and we'd taken, we'd won a couple of weeks' notice before that, something like that happened before. There's a pattern building up here. So what's happening is that different actions are kind of triggering these steps through the process, and we're collecting this data. We're collecting the results of these tests as we go through. As I described, this was a financial trading exchange. Performance was a business critical aspect of this system. It's a low latency system. And so we had two stages of performance testing here. We did component performance testing and system performance testing. Component performance testing, we kind of identified performance critical aspects of the system, and we would write things that would test that would fail if those performance critical aspects of the system fell below certain performance thresholds. That way, if I did something stupid which slowed down a messaging system or a journaling system, you know, I get an indication during the performance test that it all worked, but I just slowed it right down. That's great for the things that you know are likely to go wrong, but the system level performance testing catches the things that you don't know are likely to go wrong. That's kind of the more complex. This is sort of a whole system. For our system level performance testing, we had exactly the same hardware configuration, same operating configuration, same networking, all of that sort of stuff, so that we could precisely recreate the performance characteristics of our production system in the performance critical parts of the system, so that we could evaluate those. And we would kind of put typical days load through the system and scale it up and see whether our thresholds were with that. So as we're progressing through here, if all of these tests are passing, we're building up confidence in our release candidates. We're getting a better and better picture of where our release candidates stand. At the point at which we're approaching production, what we haven't yet tested is that this version of the system, this release candidate, works with the current version of data in production. So we want to evaluate that as well. So we would, in this environment, we would take a cut of the production data, we would anonymize it because it's financially sensitive, and we would start up the application again with that data. And part of our deployment tools were to migrate the data to the new version, whatever that meant, for the changes in the data structures that were involved. We would migrate the data, and then we'd run a series of automated tests that just prodded and poked the key use cases in the system to show that we hadn't compromised any behaviour of the system. Now, we can never prove through testing that software is good. We can never have enough tests. But what we can do is, if one test fails, we know that it's not good enough and we can throw it away. This is kind of the principle of falsifiability, which is another one of those things that we learn from science. We can't prove that all swans are white, but as soon as we see a black one, we can disprove the statement that all swans are white. So, we want lots of tests in order to have enough to give us a sense of confidence, but we also want to make sure that if a test fails, we trust that test to be telling us that something's broken, and so we want to prevent our ability to release software given that breakage. So we automate, so generally we'll automate those gates and stop us releasing software when stuff breaks. This whole process, as I said, is called a deployment pipeline, and I'm responsible for naming it as a deployment pipeline, and because I'm a geek, actually it doesn't mean the kind of pipeline, it's not a straight line thing. What this reminded me of was, this is a branch prediction line, and what this reminded me of was instruction pipelining in processes. So what's happening is that at the point at which these guys commit a change, they're taking a gamble, they're making a guess. They're saying, if I get a positive result from commit, I'm going to assume that after that everything's going to be good. And so I'm going to move on to working on new things. Meanwhile, in parallel with them working on new things, we're going to do these more expensive evaluations through this process, and we're going to figure out whether there's anything that these guys didn't think of and flag it and stop that release candidate if we find a problem. At that point, they've lost their bet. They've got to drop what they're doing, they've got to switch mind context back to where they were before, figure out what's going wrong and fix it. They've lost the gamble. However, if it all goes through, then they've won the bet, and all of this evaluation is happening in parallel with them doing more stuff. One of the pushbacks that I get from when I talk about this stuff is, okay, so this is fine. This can probably work for small projects. It sounds wonderful, but it couldn't possibly work on any scale. And my answer to that is the Google build process. So Google apply a form of continuous delivery. They've taken the interestingly different decision, as Facebook, of having a single monolithic repository. All of Google's software, essentially, with a few exceptions, all of their software is in one repository. It's treated as one thing. The nice thing about that is that it means you don't have a complex dependency management problem, because at any given point there's a coherent picture. If all of the tests pass, across all of the Google stuff, all of the stuff works together. The downside with that is that you've got to be really smart in being able to scale up all of your tools and infrastructure to create a repository that's so humongous. They have 60 million builds a year and growing exponentially. This data's a couple of years old, so I'm not quite sure where they're up to today. 100 million lines of code, all tests are run on every commit, and there are more than 20 commits per minute. 100 million test cases are executed every day. So if you have a problem that's bigger than that, it's possible that continuous delivery doesn't scale. But I think that mostly, I think this is our best data point so far. The other pushback that I get from time to time is, okay, but this is ridiculously risky. I have all sorts of horrible problems when I release software, and I can't imagine taking the risk that many times. You know, if you're releasing that frequently, you'll be broken all of the time. To that, the answer is the Amazon process. So Amazon also adopts a continuous delivery style approach. They have high levels of automation, automatic deployment, all these sorts of things. And then the mean time between deployment on the Amazon system, ecosystem as a whole, is there's a deployment once every 11.6 seconds. That deployment, on average, goes to 10,000 servers. Since they've started doing this, they've collected the data and they've had a 75% reduction in outages covered by release, a 90% reduction of time spent on outages, and only 1,000th of the deployments actually cause an outage. And there's been a massive reduction in complexity of their software systems since they employed this. This provides a pressure to simplify. This provides a mechanism to get to more reproducible, more modular, better designed systems. The last pushback that I commonly get is, okay, so this may work for simple web applications and all that kind of stuff, but my technology is way too complex for this. And my argument for this is the HP LaserJet firmware team. So in 2008, HP were in a pretty dire position. They had 5% of their total development effort was spent on what they called innovation, actually doing new stuff, any new development. They got to the stage where the business had stopped asking them for new features at all, because they never delivered them. They spent 25% of their effort porting code. The reason for that was because they had common code base, theoretically, but each device, each LaserJet device, had its own branch. And so, anytime they made a change, they'd have to then port that change to all of the other branches for all of the other LaserJet devices. They spent 25% of their effort, 5 times the effort on what they were doing for new things, on product support, which suggests they also had a quality problem. So the interesting thing about the HP case, you remember I said about the parallel evolution, this is the case. So what they did is that they just took a step back, and they hadn't read anything about lean processes, agile processes. The continuous delivery book had only just been published, but not when they started this. It was the continuous delivery book was being written there, so they hadn't got a model for this other than they knew they wanted to do better, and so they started optimizing to get ideas into production, and they started being rigorous and experimenting with their processes and techniques and technologies to do this. There's a really good book about this, which I'll show you a picture of in a minute, which is well worth reading. It's not very detailed, it's not very technical, but it gives you a really good flavour of kind of taking an existing organisation through a process of change, this kind of radical change, and then the advantages that you get out of it. At the end of this, they got to 40% of their development efforts is now spent on new things, on innovation. They spend lots more time doing testing, so automated testing, improving tools, writing tests. But they swapped out some of those things, some of the more pathological things that they were doing before. They traded those off for spending more time on being a bit more deliberate, a little bit more experimental in the things that they do. They've invested a lot in running tests in simulation so they can get fast feedback loops as part of their deployment pipeline and so on. And they're progressive, very thorough, progressive promotion of release candidates through different stages of the pipeline. Their pipeline duration is not in the order of 57 minutes because as part of their pipeline they're burning silicon, they're burning this code onto silicon. So it's kind of a day-long cycle. But even so, that is absolutely radical in that industry. And it has transformed the quality of their products, the quality of their outputs, and just the throughput of their development process. This is described in this book, which I recommend to you. So overall, their development costs reduced by 40%. The program under development increased by 140%. Development cost per program down by 70%, and the resources driving innovation increased by a factor of 5. Continuous delivery changes the economics of software development. This is not a small incremental step change. This is a fairly radical, revolutionary change in the way in which we can deliver software. Some of the most effective companies in the world use this as a process. I believe that over time, if you're not doing continuous delivery, it will still impact on you because your competitors will, and if you're in a marketplace where you're not doing it and they are, they will eat your lunch because this is a more efficient process. It feels counterintuitive, there's an investment. This is not a simple transition, but it absolutely has bottom line advantages for the companies that do it. And there's a growing body of data that backs me up that the companies that employ these sorts of techniques are bottom line more profitable than companies that don't. Times faster service restoration, higher throughput, higher reliability. And some of the data from some of these analyses, we can assert with confidence that high IT performance correlates with strong business performance, helping to boost productivity, profitability, and market share. There's a direct relationship between those things. So which organisations practice this? This is just a tiny sample of the growing body of organisations that are practicing this. And there are some organisations in there that are, no doubt you will expect to see there, and probably there are some organisations that might be surprising that are in there. So Google and Amazon, Facebook, you probably expect to see there. Nokia is interesting, HP, Netflix for sure, New York Stock Exchange, New York Times, SAP surprised me. SAP, my mental prejudice is this kind of definition of legacy systems. It's a small group, but they've been shouting about the enormous productivity gains that they've been getting in that small group using continuous delivery techniques. This is the company that was much of my presentation was based on where I worked on. Max Exchange had a reputation for being on the leading edge and very, very good at software development. And that's in no small part because we were practicing continuous delivery. And with that, I'm overrun by about 4 minutes. I apologise. Thank you.